Now, this is something that I've often wondered why the author does the way he does. Technically, this material, trig integral section 7.2, could have been done in Calc 1, right after you learned the substitution method. There's nothing that's going to be super new here, other than that you have to remind yourself of some key trig identities for integration. So I wrote them here. The key identities you're going to need pretty much for the rest of this course are, well, let's just focus on the ones I would say you have to memorize or have to have in your brain. The Pythagorean identities. So these guys right here, that cosine squared plus sine squared is equal to 1. That 1 plus tan squared is equal to secant squared. And cotangent squared plus 1 is equal to cosecant squared. Those you have to know. Like you should know them three months ago or something like that. You have to have these in your brain. You should also know how to manipulate them, right? So very common is the situation where you're going to have to exchange a cosine squared of some angle for a 1 minus the sine squared of the same angle. So that's just a manipulation of that formula. So you do have to know how to manipulate these formulas very quickly. It's going to be critical for us as we move forward. Then the other ones that you're going to have to remember are the half angle identities, or what some people call the power reduction identities. They're called the power reduction identities because if you square both sides of these, you'll get cosine squared of theta is the same thing as 1 plus cosine of 2 theta. It reduces the power, right? So that's why we call it power reduction, all over 2. And then the sine squared of theta is 1 minus the cosine of 2 theta, all over 2. You should also remember your double angle identities, but that's not going to be critical for us right now. But these are kind of the main ones you have to have in your bag of tricks. Okay. And then at the bottom here, I have the sum to product formulas. And I tell my trig and my pre-cal students, never memorize these things. Just don't, because there's a whole bunch of them. There's actually 4 of them. I just don't write the 4th one down, but there are 4 of these product to sum formulas, and then 4 more sum to product formulas. You notice I have a little superscript there, and that superscript is a footnote. And it says, of all of the trig identities, the product to sum and sum to product formulas are not memorizable. So don't put them in your brain pan. If you need them on an exam, I would give them to you. Okay, these ones right here. I don't even remember them, and I've taught them for years. It's just they're kind of obscure. Oddly enough, I can derive them. I just don't remember them. So we're going to need those. And then we're going to add a couple quote unquote basic integrals. So these are new basic integrals. And they're not so new, honestly. My 401 students already have integrated the tangent in the past, and we've talked about, or sorry, my 400 students. And you guys know as well, we've integrated this in this course. So both of these are easily provable. And in fact, I leave like a simple little line for the proof. We've actually already proven the tangent formula. So let's just see how it would work with the cotangent so you can prove it for yourself if you forget it, which is often what I would have to do when I was a student because I have a terrible memory. We know the cotangent at least is the cosine over sine. And then we can do a u substitution. Let u equal sine. So that du steals away the cosine of x dx. Notice we do have a dx and a cosine of x that can be stolen away. And so this ends up being the integral of 1 over u du. And that's the natural log absolute value of u plus c. Don't forget that absolute value. It becomes very important as we move forward. And then we know that we let u equal to sine, so that's just the natural log of the absolute value of sine plus c. The tangent one's proven the same way. You can memorize these or not. I think it's probably best to memorize them if you can. But if you have a hard time or if you know that you make mistakes when you memorize things, then just derive them as you need them. They're very fast to derive. But that guy right there is very important, or both those guys. And then these guys right here. Now, these ones are memorizable because you don't want to have to rederive them all the time. And the reason why is because the proof of these integrals, it's not a hard proof. It's just hard to start the proof. But once you start the proof, it's not a difficult proof. I will prove the secant one because, well, it's probably the most popular. The integral of the secant of x dx. Now, no matter how hard you try, a u substitution will not work here. You could write this as 1 over the cosine and let u equal cosine. It'll want to steal away a negative sign, which doesn't exist. So there's a lot of running into walls, basically, if you try to work with this. So I'm just going to give you a heads up. I would love to, in fact, do a u substitution. But the as written right now, a u sub will result in, if I let u equal secant, for example, that u sub will result in a secant tangent, which I don't have. I have a secant, but not a tangent. And you'll start running in circles. It gets really bad. So how do you do it? The trick is to multiply by the number 1. But the number 1 we're going to multiply by is a very special form of the number 1. Number 1 is like 7 over 7, 2 over 2, pi over pi, whatever it may be. In this case, I'm going to multiply it by secant of x plus tangent of x divided by secant of x plus tangent of x. And this is why I say it's not one that is easy to start because a lot of people won't see why you do this multiplication at first. But once you do multiply by this, then after you distribute the numerator through, you start to see why we did that. It becomes a secant squared of x plus a secant tangent of x in the numerator. In denominator, we have a secant of x plus a tangent of x. Now, in the numerator, I hope you can see this is the derivative of something, and so is this. In fact, this back end here is the derivative of secant. And the front end right there, that's the derivative of the tangent. Man, I wish I had a secant plus a tangent somewhere in here that I could let u equal. And I do, right? This whole entire denominator, if I let u equal that denominator, u equals secant of x plus tangent of x, then du should steal away a secant square or secant x plus tangent, or sorry, secant tangent, misspeaking left and right, plus the derivative tangent, which is a secant squared. And don't forget, there's a dx hanging off back. And let me just highlight, I need to steal a dx and the sum of secant tangent and secant squared. Luckily, I have a dx and the sum of secant tangent and secant squared to steal away. So this integral becomes the integral of 1 over u du. And we know that integrates to be the absolute value, or sorry, the natural log of the absolute value of u plus c. And in this case, u is the secant plus tangent. And we get our result. It is, like I said, not something that you would naturally have created on your own. Maybe you would have. I've had some students that can do that. But in general, that specific derivation is a little bit obscure. But the result is very important. This derivative, or sorry, antiderivative, the integral of secant, it ends up being one of the most common integrals, at least in our textbook. Also, the integral of secant cubed ends up being very important as well. We'll prove that a little bit later on. So questions on either of those theorems. I didn't prove the cosecant part because once you see the secant one, you know how to do the cosecant one. You multiply top and bottom by cosecant plus cotangent. So questions on that while I take a swig. All right. So let's use some of this. Using the basic trig identities with integration. Again, I want to remind you, this is going to be nothing new. There's no new integration trick we're using here. It's just going to be u subs with our trig identities. So if you take a look at this guy right here, and somebody says, I want to integrate this. First of all, I'm going to now list down a few tactics. So tactics. And the very first one I always will try is a u sub. Before I move anywhere else, I think maybe a u sub will work. If I could do a u sub, we have a couple choices I hope you can see. We can let u equal sine or u equals cosine. One will work and one will not. So when you're deciding which one to do, and if you read the textbook, the author gives you kind of an if this, then that situation, where he basically gives you like a bunch of steps. I don't like to follow that. I like to rather ask, maybe I'll state it this way. I would rather state something like, with trig functions, even powers are very desirable. Yeah. Very, very desirable. The reason why even powers are desirable is because of our trig identities. If you think about our trig identities, these guys right here are Pythagorean identities. Notice all the powers there are even. We would love to have even powers. By the way, even if the even power, there's too many evens in that statement, given an even power that's not the second power, these still work. If somebody said, oh, I have a cosine, sorry, I don't have a cosine squared, I have a cosine to the sixth, for example. Well, that's the same thing as a cosine squared to the third. And a cosine squared is a 1 minus sine squared. So my goal of using even powers, that's a very important goal to keep in mind when you're dealing with trig functions. Even powers are very, very, very desirable. Trig functions with even powers, that was supposed to be plural. There we go. All right. So that's kind of how I make my decision here on what I'm going to let u equal. Always envision what derivatives steal. So if I let u equal, for example, the cosine, which is, I'm going to write this in red because it's a bad choice, but if I let u equal the cosine of x, just envision before you do that substitution what du would need to steal away. Don't worry about the negativity of it. I'm not really concerned about pluses or minus signs right now. What I'm more concerned about is when I steal away a power off of the sign, will it be even power that's left over? And the answer there is no. That will reduce our integral down to an odd power on that sign, and I don't want that. If I had done that, I'd be left with this, the negative integral of sine cubed, because again, our substitution steals away a single power of that sign. So we have 3 powers left. So sine cubed of x. And then cosine cubed, well, that's just times u cubed. And I cannot touch an odd power of a trig function. It's unfortunate. It's just how it works. So that red ink is there to tell you that's a bad substitution. On the other hand, if you were to do u equals sine of x, just think about what du will steal away. It'll steal away a single power off of this cosine, which will make it an even power in the end, and that's exactly what I want. Now, you may think, well, why does he want an even power on that? I mean, how is that going to help us? Well, you'll see. Our integral will become, let's see, it's a sine to the fourth, but sine is u, so u to the fourth. I'm going to steal away a power of cosine and the dx, and I'll replace that power of cosine and the dx with a du, and I'm left with 2 powers of cosine left over there, 2 powers of cosine of x. Now, it's a mixture of variables. I totally get it, but because we were lucky enough to deal with even powers on that cosine, I can rewrite it in terms of the sine. And the sine, remember, is u. So this is going to be u to the fourth the integral of u to the fourth times 1 minus u squared du. And then you just distribute and you integrate a polynomial. U to the fourth minus u to the sixth du, and integrate. That's u to the fifth over 5 minus u to the seventh over 7 plus c. And remember, in the end, you want to resubstitute back in. You didn't start with u's. You're not going to end with u's. Resubstitute in sine of x for that u. So this will be sine the fifth power of x over 5 minus the seventh power of sine over 7 plus c. And that is the antiderivative of sine to the fourth times cosine cubed. We didn't use any new integration techniques. We just used a u sub. Just because it's a product of functions doesn't mean it's always going to be a by parts. Try a u sub first. And that's actually what this full section is about, is do u subs on trig functions first. Take advantage of even powers if you get them. Questions in there, and I'm going to mention something in a few moments, but questions in there on any part of the substitution process, or the goal, right? Even powers. That's a really good key. Okay, so if somebody's going to be typing something, I'll just I'll keep my eye on the chat. Why didn't they use sine to the fourth of x? Yeah. So it would kind of go along with what I've said in the past, right? When you do a u sub, do it for the largest piece you possibly can. Well, the problem here is if you let u equal sine to the fourth of x, then du by the chain rule would be 4 times sine cubed of x times the derivative of sine, which is the cosine of x, and then a dx. It just, I don't know why, it just looks really nasty to me, right? So not only that, but actually that doesn't help you, because my dx is going to steal away a cosine, fine, steals away a power cosine, and then 3 powers of sine. And I do have 3 powers of sine to steal away, and then I don't have a 4. I can move the 4 over, that's fine. But then I'll be left with a sine of x times a cosine squared of x times a du. And that sine of x, I suppose I could say, well, that's the 4th root of u, but it starts getting really messy. So in this case with trig functions, I try my best just to keep it simple. It is a good question, though. It's a really good question, but I try to keep it simple when it comes to trig functions, because the substitutions can get very gnarly because of the chain rule. Yeah. Something to note on the homework, by the way, and I do, if I've coded the problems, I do mention it in my coding, that if you have an answer like this, if it's a square, you could totally use this notation. But anything other than a square, it will not accept. So when you're working online, you would write it this way: sine of x, and then to the 5th. Okay, so I'm just letting you know that that's something that you have to pay attention to in the online environment. If I've coded the problems, which I've had to code like 7 or 8 different problems for this homework assignment, I've put the note in there that that you'll want to write your answers like that if you have high powers. Okay. Now we only have 3 minutes. I just want to see if there's anything interesting. There is. We could do this easily in 3 minutes. I would like to. I know you guys, I love to squeeze every second out of the class. So look at this guy right here. Sine to the 7th. If you are going to say that that is sine to the 8th of x over 8 plus c, I'm going to say you're wrong. That trick of adding 1 to the power and dividing by the new power only works with polynomials. Nothing else. Absolutely nothing else. So in fact, it really only works with just x, not like, it just works if it's just x, basically. So it's not that. So the easiest way to do this is to force that power to be even. Force to be even. And you may say, how are you going to force that to be even? With a u substitution. It is often the case when you do a u substitution that you substitute in for something that's not even there. If I allow u to equal the cosine, its derivative, forget about the negative for a moment, its derivative will steal a single power away from the sine, reducing that to a 6th power, which is exactly what I want. It's a really cool little trick. If you do that, your integral becomes the integral of, well, dx times sine of x will be traded out for a negative du. I stole 1 power off the sine, so I only have 6 powers left. And I said cosine of u, but there's nothing else in here that I need to substitute in for, right? There, I've already substituted out the dx for a sine of x du and a negative. And then I'm left with 6 powers of sine, and there's nothing else I need. But you see there's a mixture of variables. How are you going to fix that? Well, remember, sine to the 6th is the same thing as sine squared to the 3rd. And sine squared is 1 minus cosine squared. And cosine was our original substitution. So that's going to be 1 minus u squared in that integral. The quantity 1 minus u squared cubed du. And now you can multiply that all out. I'm going to use the Pascal's triangle to quickly multiply it out. And now you can integrate. It's a really nice way of doing this style of problem. 3/5 u to the 5th minus 1/7 u to the 7th plus c. And then remember, u was the cosine. So I'm just going to substitute in cosine and I'm done. Negative cosine of x minus cosine cubed of x plus 3/5 cosine to the 5th of x minus 1/7 cosine to the 7th of x, and then plus c. A very simple looking, I suppose, integral, sine to the 7th, but its value is terrible. Nobody would have guessed that the antiderivative of sine to the 7th is that ugliness down there, but it is. So anyhow, there's a good showcase of how u substitutions kind of grow in complexity as we move forward. I've kept you a minute over. I apologize. So I will be back in about 9 minutes to start up office hours. If you are not there, then I will see you on Wednesday. Otherwise, I'll be back, like I said, in 9 minutes. Have a wonderful day if I don't see you.